Okay, we have completed drawing all of the structural elements, which marks the completion of the first part of the modeling phase. Now we need to assign and create the remaining things. But before we proceed, I would like to share with you this text file that discusses the stiffness of the members I will be using. And as the name reveals, IG refers to the gross moment of inertia of in-plane bending of walls. I will use these modifiers inside this model to create a linear model that have the same initial stiffness of the nonlinear model created in Perform 3D software, okay? And to provide more details and explanation, I would like to open this PowerPoint presentation to show you what I exactly mean. Okay, this table presents the stiffness values of the members to be used in both linear and nonlinear model. To create a linear model that have the same initial stiffness as the nonlinear model, we need to use these values here for that reason. Maybe the only unclear thing is this one, the fiber section. And for that, let me proceed to the next slide to show you what the meaning of fiber section. A fiber section is a mathematical representation of a cross-section as shown here. It divides the cross-section into a series of discrete elements, each having its own properties like inertia, percentage of reinforcement, strength, area of concrete, and etc. The fiber section also considers the combined effect of the axial force bending interaction on the behavior of the member. It allows us to determine the stress distribution and deformation characteristics at different points within the cross-section. Also, we can assess the axial force bending interaction, the influencing factors such as the capacity to resist both tension and compression, and lastly, the redistribution of stress along the cross-section. Therefore, if this member fails, we expect the program to redistribute the force inside the system. Therefore, we are expecting to have degradation in stiffness due to cracking. This is actually the idea. Okay, I think the idea should be clear now regarding the stiffnesses of members and why I need to use these modifiers inside one of my ETABS model. And let me repeat, we need to check the effect of stiffness degradation on the overall response of the studied structure. And to provide you with more complete understanding of the idea, let me show you this example based on same height building. I have applied here several seismic analysis methods, but let's just focus on the first and the last method. The first is nonlinear response history analysis, and the second is linear response spectrum analysis. And I'm referring to it as NLRHA because I'm applying this method in a linear model inside ETABS, which have the same initial stiffness as the nonlinear model, okay? Therefore, all the results obtained from response spectrum analysis that is applied in a model that having a stiffness same as the nonlinear model, I'm referring to them as linear response spectrum analysis NLRHA. Therefore, let's do the comparison between the first and the second or the last method. If we check this graph, for example, here there is a degradation in story shear as shown, is due to the nonlinear actions happening locally to each member. And similarly, if we check here the floor displacement and do the same comparison, we will find out that linear response spectrum analysis provides lower results of floor displacement, maybe due to the higher structural stiffness. Therefore, as the structure undergoes more cracking, as it becomes more flexible, resulting in higher displacement and less forces. Okay, this is actually the benefit of using these two lines. Okay, let's now change the flexural stiffness of members inside ETABS software. I will do the columns first. Going to this option, Modify Show Modifiers, we need to do some changes here, okay? Going to this table again, and for columns, I'm using the fiber section inside the nonlinear model. But the one thing that I didn't mention for you regarding the columns, that I will use two types of cross-section to model this column inside Perform 3D. I will assign a fiber section at the ends, while I will assume that the remaining portion here at the middle will remain in the elastic range, okay? Therefore, I will reduce the stiffness of this elastic element inside Perform 3D to be 0.7, okay? And that's why I will go here now and I will change the inertia to 0.7 for columns. Okay, now we have finished changing the modifiers of the columns. Let's do the slab section by clicking here this option. And as shown here, those terms have been changed, or they are different from the columns cross section. Actually, let's agree for now. Let's say that the terms with F corresponds to the modifiers for the in-plane banding, and the M's here correspond to the out-of-plane banding, okay? And as shown here in this PowerPoint, for slab elements in plane, we need to use just the full gross moment of inertia, while for the out of plane, we need to reduce it to 0.25 of gross moment of inertia, okay? Therefore, for the out of plane banding, we need to type 0.25, okay? And that's all for the slab element. Lastly, we need to do the walls. Let's go again to this PowerPoint. We are using the fiber section to monitor the in-plane banding of the shear walls, while for the out-of-plane banding, we will reduce the flexural stiffness to 0.25 of the gross moment of inertia, okay? Therefore, we need to go to here to ETABS, and we need to change those to 0.25. The one thing that I didn't mention about fiber section, they have the gross moment of inertia at the beginning of the analysis. Actually, this section allows us to monitor the cracking or the stiffness degradation using the stress-strain diagram. But at the first time of starting the analysis, this section have the full gross moment of inertia, or the full stiffness in other words. Okay, therefore, I didn't change anything related to the modifier, okay? I didn't change it, I keep it as a 1. Therefore, we are using the full gross moment of inertia for the in-plane banding. Lastly, we have the coupling beam. And since it is a beam, we will consider it as 0.35 for the flexural behavior. Therefore, we need to go to ETABS, and we need to change F11 to 0.35, and for the out of plane banding, we need also to put or to change those bandings to 0.35, okay, and okay. I will discuss for you later on the meaning of each of those modifiers, but just for now, let's do it as I do it. And the last step actually now is just to import the response spectrum curve for this model by going to this option here. By default, there is a response spectra defined inside ETABS. We need to delete it. I will choose here the option from file. And as shown here, we need to import this text file. We need to skip one line at the beginning. Therefore, we need to specify one here. We need to browse. This is the file. Open. Here we need to put 0. Make sure to put 0 for the damping ratio. I will name this Bangkok 5%. And I'm using the damping of 5% for this spectrum because the damping of this model will be assumed to be 5%, okay? Also, we have already defined the load patterns of superimposed dead load and live load, but I didn't assign any loads till now. Therefore, let's select the floors. And from the assign, shell loads, uniform. For live load, I will provide 3 kN per square meter. Let's select the previous selection. And for superimposed dead load, I will provide 2.5. Let's save this model again. And actually, this is all what we need to do inside this model that is called IG. This model now is ready to be analyzed and to export the results from it, okay?